It's been estimated that 10% of all the world's global electricity production is used to drive air conditioning systems. It's kind of surprising. In 2020 dollars, that represents $300 billion per year. So even a 1% improvement in the efficiency of air conditioners or a 1% decrease in the load on air conditioning will save $3 billion a year, and it's probably substantially more nowadays. That's why a lot of recent attention has been focused on passive cooling, using specialized coatings or surface treatments to reject heat without using electricity. It's the principle that underlies architectural supercooling, allowing buildings and structures to actually cool below ambient temperatures. The principle that makes this possible is that all physical objects glow. They emit electromagnetic radiation. That radiation's wavelength is proportional to the temperature, and it follows a rather asymmetric curve called the Planck spectrum. The peak of that curve occurs at what's called the black body temperature. The sun, for example, at 5700 Kelvin, has a black body temperature or peak at around 550 nanometers in the yellow part of the visible spectrum. The amount of energy that it releases is proportional to the fourth power of temperature. Whoa. So 1 square meter surface of the sun radiates 67 megawatts. As surfaces cool or objects cool, this entire spectrum redshifts and moves into the infrared. When you get down to body temperature or room temperature, that wavelength peaks at around 10 microns or 10,000 nanometers. And because of the fourth power of temperature, the amount of energy released plummets down to about 500 watts per square meter. I have a body surface area of about 2.4 square meters. So I am continually radiating into the environment about 1.2 kilowatts. Now, the reason I don't end up looking like Jack at the end of The Shining is because I'm surrounded by other objects, the floors, the walls, the cameraman, that are all at a similar temperature and are radiating back to me. We're in equilibrium, with one exception, the sky. The sky is very cold. It's not at 2.7 Kelvin, the cosmic microwave background temperature, and it's not even as cold as the air that surrounds a commercial airliner at altitude. It's a rather complex temperature that represents the column of air all the way from the ground all the way out into space. But it can be as low as 50 degrees below 0 Celsius. It'll vary a little bit day and night, summer and winter, and with humidity and altitude. And you can plug these variables into the equation and come up with an average that usually runs close to about 350 watts per square meter. The result is that any object down here on the ground will lose about 150 watts per square meter into the sky. Now, there's one last principle that we have to explain before we get into the demonstration. It's called emissivity, and you can think of this as sort of the inverse of reflectivity. It represents the percentage that any real surface, any real object, will radiate compared to a perfect black body emitter, which doesn't exist. Typical objects like skin, cloth, commercial paints, concrete, wood, plastics, all have emissivities that run around 75 to 85%. Certain materials that are very reflective in the infrared, like polished metals, like aluminum, have very high reflectivity and as a result, lousy emissivity. A polished aluminum is around 6%. So if we took me and placed me inside of a large aluminum box that's just open to the sky, even if the box and I are at the same temperature, the box is not going to radiate very much infrared. I will lose infrared to the sky, and any infrared that I give off will be bouncing off the surfaces of the box and go into the sky. And I will lose about 150 watts per square meter. So I will actually lose about 370 watts, my body heat, into the sky. And I'll feel that because the basic basal metabolic rate of the human body, when you're not doing anything, you're just sitting, watching a YouTube video, is about 150 watts. That's more than double that. So to demonstrate that, to show that this works and maybe how you might be able to apply this to something useful, we built this. This structure consists of a radiator that we place inside of an insulating box. The box is made from rigid polyurethane foam. It's an excellent contact or thermal insulator. And then we covered it with aluminum tape. This tape here that we use for this purpose is not just colored as aluminum. It's pure aluminum. It has about 6% emissivity in the infrared. The result is that by surrounding this radiator surface with this insulated box, we're able to isolate it from the environment and also prevent infrared from being radiated down onto this very specialized surface. To build up the box, we put a back panel behind this radiator that we built, and later we'll show you how we made this structure that will transfer heat between water and the air. And then we surrounded it with a modular structure that lets us build up the walls around this box to surround the radiator. Like this. You'll also see that we have a little input port here and an opposite port in the other corner that allow water to flow into the radiator and flow out of the radiator in a closed loop. I'll show you how that works in just a sec. Now, because we are not in big sky country or on top of a building, the trees and the surrounding buildings will be able to radiate some infrared down on this test surface and decrease the effectiveness of this test. So we built a little extension to this box, which acts as an infrared barrier to the surroundings and simply sits on top like this. With this, you really can't see the buildings and the trees. The final part of this assembly is the fact that because we're going to actually try to cool this surface off below ambient temperature, wind and airflow that moves past this will mitigate that difference. And so in order to prevent that, we could either build this box very tall so that we get stratification and we get air to sit at the bottom, the nice cold air. And that will provide good insulation because air is a superb insulator when it doesn't move. It's what makes polyurethane foam a good insulator. It's not the plastic, it's the air bubbles. But that would be pretty bulky. So then the final step was to build a window. This window consists of an aluminum frame on which we stretched a plastic film to act as a barrier to airflow and allow the air to stagnate inside of the structure. The plastic is kind of interesting. If you use glass, plexiglass, polycarbonate, it will absorb the infrared. It's not transparent to allow the infrared to go up into the sky. Turns out, this stuff, plastic wrap, polyethylene is extremely transparent to the infrared, and so it can radiate out right through this but prevent airflow going across it. And it's lightweight and it's very convenient. I'm going to show you how we put this heat exchanger together because it was a rather interesting project. And we filmed that a little while ago. So I think you might want to take a look. How did we build this? It's based on these neat little devices that you can get on Amazon that include an input and an output for flowing liquid, and then have flow channels inside of them that allow them to distribute or take the heat and send it into the fluid. They're really nice, they're inexpensive, you can adhese them, you can use an adhesive to bond them onto CPUs, lasers, LEDs, and because they're so cheap, you can just permanently bond them, which makes them a lot more robust and easy to work with. Problem is, they just don't get big enough. We needed a 1 meter surface area, 1 square meter of surface area. So using that same sort of design, we built this. And let me show you how it's put together. I took some aluminum U-channel and miter cut the corners and welded them to form this rectangular structure here. And then bored a couple of holes in opposite corners, placed an aluminum fill tube and exit tube. And then once it was inserted into the hole, I then took some toughened epoxy and floated around the outside of the tube to make it nice and rigid and provide a leak-free seal. This frame then is located on a piece of 1 millimeter thick sheet aluminum that acts to seal up the bottom surface, and there's a mating 1 millimeter thick piece of aluminum sheet that fits on top. Now, one of the problems with this kind of a system is that with a 1.5 centimeter thick, 1 square meter area, this thing would contain, when full, 15 liters of water. It would weigh a lot. So on the surface that doesn't matter, we're not doing the heat exchange, I bonded some closed cell foam to fill up the bulk of the volume inside of here to keep the panel light when it's filled with water. But because these foam inserts are not as thick as the spacing here, we still get a water layer between the front surface and the aluminum, so we get good thermal exchange. Now we could just weld this whole thing together. Problem with that though is it's a lot of welding. You'd have to weld the entire periphery twice. And then we would have to weld in these stiffening ribs that I've placed in between here to provide reinforcements so that the sheets don't balloon in and out with pressure changes. And those aren't visible, so we'd have to do some spot welding. So for this very low load application, we decided rather to use epoxy bonding, and that's how we're going to put this together. So after thoroughly cleaning off the contact points, then sanding them, and then cleaning them off again, we've got the whole thing mounted on a table, and I'm going to use some of this toughened epoxy from Loctite. It's good stuff. It's a lot more expensive per gram than if you mixed up a bucket of this yourself. But in these syringes, they're very nice and neat and easy to work with. And this particular material is also useful because it has some rubber powder in the mix that makes this a toughened epoxy. So it's much more resilient and flexible and will not crack as easily as the pure epoxy resin. It's also super for bonding surfaces that have different coefficients of thermal expansion, like glass to metal, because it can take up some of that differential expansion. So with that, I'm going to start by putting on some gloves, and we're going to get this thing going.
See, this is the part actually I would have wanted to do because I wouldn't need to do.
You may have to. My hand's killing me.
I wouldn't mind.
Okay, then you see how I'm doing this? You can do the next.
Well, I may as well come in. Why not?
Why don't you? You can help me with the frame. We're going to put that down in just a sec.
Yeah, I just want to see how you're.
Okay. This, if you hold that side there. Okay, we're going to put this down and go real close, but like an inch away.
Now you want the frame to line up exactly with what's there, not overlapping, not anything.
Yeah. Should be just about right.
How's this?
Let me see. It's perfect.
What about this side? I mean, it should be fine.
Yeah, it's perfect. Okay. So if you want to put on some gloves.
Yeah, I'll do start.
Yeah,
give me a second.
Waste time.
It doesn't matter if I'm quite like a line.
No, it doesn't. It all ends up smoothing out. You'll even see that where you began, how smooth it got. Just make sure it
Because I
stays
want to go
about.
as fast as possible.
Right, but you don't want it too thin. You're doing well. I mean, you're doing it perfectly. All right, took us about an hour, and the old adage, you can never be too rich, too thin, or have too many clamps. These iron rods on top are just compressing the glue on the ribs to make sure that we get good adhesion between the ribs and the surface sheets. And the tape that was placed around the edge is simply to retain any of the extruded epoxy so that we didn't end up covering our clamps and the floor with a bunch of epoxy that drips out. Aluminum doesn't absorb epoxy like wood or fiberglass, and so you really don't need very much in order to coat a surface. We wanted to be very generous on the outside because any kind of a leak, it'd be a disaster. So we really wanted to make sure we had a good epoxy seal. So now we're going to leave this 90-minute working time epoxy a couple of days to really harden up. Then we're going to fill this thing up with water, cross our fingers that we don't get any kind of leakage, and then we'll move on to the next stage, which is to put the super coating on it. Now soon we're going to show you the heart of what makes this work is the special coating. Because if the aluminum itself were just exposed to the sky, just like the walls, it would not emit very efficiently, and the coating makes all the difference. This is not white paint, it's a special super coating. And we're going to show you not only how it works and why it works, but actually how you can make it yourself. It isn't that complicated. Now, to demonstrate that this process actually does work, what we did is I hooked two rubber tubes up to the heat exchanger on the two ports that are located at opposite corners. One side goes to a submersible pump that's immersed inside of a vacuum dewar that effectively blocks all thermal transfer between the outside environment and the inside, which is going to be filled with water, which will circulate in a loop between and back to the reservoir. Inside of the reservoir, I have a thermocouple, a temperature gauge, and this is going to read the temperature over here, and we're going to watch the temperature change as we put this out under the sky. If this works, the temperature of the water will actually drop down below the surrounding air temperature. So we're going to see if that works. This is the power supply that's going to be operating this, and we're going to get this going outside. So we're going to put on a couple of jackets and we're going to head out. All right, we're set up outside to test the large 1 square meter panel under the clear sky. And what I have over here is a power supply that powers the pump. I'll show you that in just a sec. We have the temperature probe that's measuring the temperature of the liquid that's being constantly recirculated through the heat exchanger and into that silver dewar below that contains the reservoir of the water. The water has a small amount of propylene glycol in it because we are going down to such low temperatures. We don't want the water to freeze in the heat exchanger. You'll also see that I have this upper collar on the box here. This is because we aren't on top of a building or in big sky country. We have a lot of trees and buildings and structures around here that can all radiate infrared radiation down onto the panel. And we want to do the best we can with this chiller to make sure that it only sees the sky. It can radiate its infrared out, but it doesn't get bombarded by infrared from the surroundings. Now, the temperature at the bottom here is the outdoor temperature, which right now is at, if I can see it, 0.5 degrees Celsius, and the temperature of the probe in the circulating liquid is at 0.9 degrees Celsius. So we're just going to let this go for a while and see where we get. Okay, so as you can see, there's a pretty significant difference between the outside air temperature here and the fluid that's circulating through the chiller. And you might wonder, how could you apply this to cooling off a structure or a building? There's a couple methods. One, if you have a hydronic heating system in your home or your building where you have a boiler that's flowing warm water through radiators or your floor, you could tee in the fluid from this in order to be able to cool those structures in the summer. That would allow you to maybe eliminate or minimize or supplement your normal air conditioning system. Another method might be if you have a split cycle air conditioner or a heat pump where the compressor outside compresses the refrigerant and then dumps the majority of the hot refrigerant heat into the radiator using the large fan outside the structure. You remember that you can't get that fluid temperature even as low as the outside air temperature. It can never equal the air temperature. So what you could do is place that or flow that liquid that's come out of your radiator after it's dumped the majority of its heat and put it through a heat exchanger, a liquid-to-liquid heat exchanger, where you circulate some of the fluid from the chiller around the refrigerant after it's dumped most of its heat, fooling your air conditioner system into thinking it's a little bit cooler outside, boosting its efficiency, and you still retain all the benefits of the heat pump or the air conditioner in dehumidifying or producing additional cooling during times when this system may not be operating at full capacity. One of the limitations on this kind of a system is clouds. The base of a cloud is not as cold as the clear sky when you can dump the infrared radiation all the way up into space. The other thing you may be wondering is, obviously we're talking about very low temperatures here. We're below freezing. This kind of a system actually becomes more efficient the hotter it becomes, because the sky temperature increases in the summer, but not nearly as much as the ground temperature does. And so with a larger differential, you're going to see an even greater cooling potential, because remember, temperature to the fourth power. If you increase the temperature of this panel just 10%, you'll increase the amount of heat it dumps into the sky by 50%. The other thing you may notice is we're doing this at night, and you might think, okay, this thing is only going to work half the time. Well, solar panels also only work half the time, and we spend billions of dollars a year on solar panels. Interestingly, though, because of this super coating that we have put on this system, we can operate this 24 hours a day, even in bright sunlight. And that's what we're going to show you in the next video, how we made this super paint that makes this possible. In addition, we'll then test this kind of a system in the sunlight to show you that it can work 24 hours a day. So I hope you found this interesting, and I hope if you found the kinds of stuff that we're covering here interesting enough, you'd take a couple of seconds and subscribe. It really helps out the channel, and the bigger we get, the more we can afford to build and to bring you in our videos. So I want to wish you a very good evening. Take care. Thanks a lot for watching, and I'll see you soon.